The algorithms we've looked at so far don't make any assumptions about the data they're sorting. We can sort integers, floats, strings, objects, anything. The algorithms don't assume a certain data type. Specific implementations do, but not the algorithms themselves. They also don't assume that the data being sorted is bound in any way. For example, they don't assume that all the values being sorted will be less than 100. There are algorithms that do make assumptions about the data being sorted, and because they make assumptions, they can sort the data more efficiently. In fact, they can achieve linear time, O to the n complexity. And so the next couple of algorithms we're going to look at make assumptions about the data they're sorting. And the first algorithm is called counting sort. So counting sort makes assumptions about the data that it's sorting. It assumes that all the values are discrete and they're within a specific range. So this algorithm only works with non-negative discrete values. We can't sort floating point numbers. We can't sort strings because they don't have discrete values. So practically speaking, you'll usually use this algorithm with whole numbers. So the way it works is it doesn't use comparison, so it doesn't actually compare values in the array against each other. Instead, it counts the number of occurrences of each value. And you'll see how it does this when we go through the algorithm for a specific array in just a minute. Now, as I said, values must be within a specific range, and the range has to be reasonable. It can't be huge. You're not going to use counting sort to sort values that are between 1 and 1,000,000, for example. Now, our array, the usual array that we've been using, is not a good candidate for counting sort. It has negative numbers, so we're going to use a different array to go through this algorithm by hand. And so this is the array we're going to use. We're going to assume that we're sorting values that are between 1 and 10 inclusive. So the values can be 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. We have 10 possible values. And so what we do is we create a counting array of length 10. So this is going to be a separate array from the one that we're sorting. And then we traverse the input array, the one we're sorting, from left to right. And using the counting array, we track how many of each value are in the input array. And then once we've traversed the entire input array, using the counts in the counting array, we write the values in sorted order back to the input array. And so we're going to sort the array that you see on the screen. And so when I equals 0, we're going to look at the value at position 0, and we see it's 2, and so we add 1 to the counting array at position 1. Because we know the values are between 1 and 10, in the counting array, position 0 is going to hold the number of 1s we find. Position 1 will hold the number of 2s we find. Position 2 will hold the number of 3s we find, etc. And so in the first position, we found a 2, so we increment counting array index 1. We increment it by 1. Then we're going to increment I to 1, and at the input array position 1, we have a 5. So we're going to increment counting array 4 because that's where we're counting the number of 5s. We increment I to 2. We have a 9. So we're going to increment counting array position 8 by 1 because we found 1 9. When I is 3, we have an 8. So we're going to increment counting array 7 by 1. At position 4, we found another 2. And so we're going to increment counting array 1 by 1. So now we have 2 there because so far we've seen 2 2s in our array. Next we find another 8. So counting array 7 will be incremented by 1. So we now have a 2 there because we've seen 2 8s. Then we find a 7. So we're going to increment counting array 6. We found a 10. So we're going to increment counting array 9. We found a 4. So we're going to increment counting array 3. And finally, we find a 3, and so we're going to increment counting array 2 by 1. And so at this point, we've traversed our entire input array, and we have counted how many occurrences of each value we've seen. And so what we want to do now is, using the counting array, we're going to write back the values to the original array. So in this slide, the counting array is at the top, and the input array is at the bottom after we've written it back. So the way this would work is we'd traverse the counting array and we would say, okay, so there's 0 ones, and so we don't have to do anything. We just move to the next position in the counting array. Okay, there's 2 2s, and so at this point we're going to write 2 2s into the input array. And then there's 1 3, so we'll write 1 3 to the input array. There's 1 4, so we'll write 1 4 to the input array. There's 1 5, so we'll write 1 5 to the input array. There are 0 6s, so we don't do anything. There's 1 7, so we write 1 7 to the input array. There are 2 8s, so we're going to write 2 8s to the input array. There's 1 9, so we write 1 9 to the input array. And finally, there's 1 10, and so we write 1 10 to the input array. So essentially, counting sort has 2 phases. The first phase is we traverse the input array and we count how many of each value we have. And then in the second phase, using the counting array, we write values back into the input array. And so as you can see, our input array is now sorted. And we didn't do any comparisons. We didn't compare any of the elements against each other. We're just merely counting how many of each value we have, and that's why the algorithm is called counting sort. Now, this is not an in-place algorithm. As we've seen, we have to create a counting array, and the length of the counting array will depend on the range of values we have. And because of this, counting sort is best used when the range of values you have is around the same length of the input array. So if you have an input array of 20, ideally the number of values that there are, you want to be around 20, because think about it, if you have an array of 10 elements and the range of values can go from 1 to 10,000, then you're going to have to create a counting array of length 10,000 to sort 10 elements, which would obviously be ridiculous. So counting sort works best when the range of values that you can have, the number of values in that range is roughly equivalent to the number of values that you want to sort. So in our case, we had a range of 10 values and we had an array of 10, so it was perfect. As I mentioned, this algorithm can achieve linear time, and it can do that because it's making assumptions about the data. And so because it can make these assumptions, it can achieve linear time. Now, the counting sort I showed you is unstable. If we want it to be stable, there are extra steps we can take with counting sort. Instead of just incrementing a counter, for example, you would perhaps use what's called linked lists in the counting array. We're going to cover linked lists later. Okay, that's it for learning what the counting sort algorithm is. Let's go ahead and implement it. I'll see you in the next video.